Hello students, myself Sarama Malik, Assistant Professor of Gargi Memorial Institute of Technology. Today I discuss about some theorems on graph theory. In my previous lecture, there also I discuss about some theorems. So here I discuss about also some theorems. Now, theorem number 7. A simple graph with n number of vertices and k number of components can have maximum n minus k into n minus k plus 1 by 2 number of edges. Okay, so we have to prove this. Now let each of the k component of the graph contains n1 into up to nk number of vertices respectively. Okay, so we have n1 plus n2 plus up to nk, that is equals to n. Okay, and here ni is greater than is equals to 1. Okay, so now we prove here. Now we have to prove the inequality summation of I is equals to 1 to k in I square, this is less than is equals to n square minus k minus 1 into 2n minus k. We have to prove it. Okay, so we know that summation of I is equals to 1 to k in I minus 1. What is this? This value is equals to summation of I is equals to 1 to k in I minus summation of I is equals to 1 to k 1. Okay, this is the summation of n I. We know this value is we write here n, that is this is n, minus this is the k times of addition of 1, so this is equals to k. Okay, so we got it n minus k. Okay, now if we square this, that means whole square of summation of I is equals to 1 to k in I minus 1 whole square, this is equals to n square plus k square minus 2nk. Okay, so we have this is equals to summation of I is equals to 1 to k in I minus 1 whole square plus summation of I not equals to j, double summation, in I minus 1 into in j minus 1. Okay, this is equals to n square plus k square minus 2 in k. Okay, so from here we can write summation of I is equals to 1 to k. This is written as n I square minus 2 n I plus 1 plus, this is the double summation of I not equals to j, in I minus 1 into in j minus 1 is equals to n square plus k square minus 2 in k. Okay, now this is equals to, if we split this one, this will be summation of I is equals to k in I square minus 2 into summation of I is equals to 1 to k in I plus summation of I is equals to 1 to k 1 plus double summation I not equals to j in I minus 1 into in j minus 1 is equals to n square plus k square minus 2 in k. Okay, now from here we can write that this equal to this is the summation of I is equals to 1 to k in I square. This is the same, and from the second part this is 2n plus k plus, this is also same, double summation of I not equals to j in I minus 1 into in j minus 1. Okay, this is equals to n square plus k square minus 2 in k. Now from here we can write summation of I is equals to 1 to k in I square minus 2n plus k. This is less than is equals to n square plus k square minus 2 in k. Okay, this value plus this one equal to this. Now if we out this one, that means this one is less than is equals to this one. Okay, so here we can write as in I minus 1 is greater than is equals to 0 and in j minus 1 is greater than is equals to 0. Okay, so from here we can write summation of I is equals to 1 to k in I square, this is less than equal to n square plus k square minus 2nk plus 2n minus k. Okay, so that means this summation is less than is equals to n square minus of k minus 1 into 2n minus k. So the one is proved here. Okay, now we prove here the inequality. Okay, now if we let gi be the component of g having n I number of vertices, then the maximum number of edge in gi is equals to number of possible edges joining any two vertices. Okay, that means since there are no parallel edge or self loop as the graph is simple. So there exists exactly one possible edge corresponding to any two vertices of GI. So maximum number of edges in GI, that is equals to number of selection of two vertices from Ni, that is equals to NIC2, which is equivalent to Ni into Ni minus 1 by 2. Okay, so the maximum number of edges in G is summation of I is equals to 1 to k in I into Ni minus 1 by 2. Okay, so this is equals to half into summation of I is equals to 1 to k in I square minus in I. Okay, so that can be written as half of summation of I is equals to 1 to k in I square minus summation of I is equals to 1 to k in I. Okay, and we know this value from the equation 1. So this is less than is equals to half of n square minus of k minus 1 into 2n minus k minus this summation is n. Okay, so which is equals to half of n minus k into n minus k plus 1. Okay, so this is our theorem. Okay, there is another theorem also. A connected graph is an Euler graph if and only if all vertices of G are of even degree. Okay, so a connected graph is an Euler graph if all the vertices are of even degree. Okay, this is not in your syllabus, so this proof is not is in your syllabus. So if only you remember the statement. Okay, now we illustrate some examples here. Number 1, find the minimum and maximum number of edges of a simple graph with 10 vertices and 3 components. Okay, so So minimum number of edges, we know it is n minus 1 when for n number of vertices when it is one component, and as it is here k components, so minimum number of edges n minus k. Okay, so minimum number of edges is equals to n minus k, that is 10 minus 3. Okay, and maximum number of edges is equals to, from the previous theorem, that is 10 minus 3 into 10 minus 3 plus 1 by 2. Okay, so as we know that minimum edge is less than is equals to number of edge is less than is equals to maximum edge. So 10 minus 3 is less than is equals to number of edge is less than is equals to 10 minus 3 into 10 minus 3 plus 1 by 2. That means 7 less than is equals to number of edge less than is equals to 7 into 8 by 2, that means 28. So the minimum number of edge is equals to 7 and maximum number of edges is equals to 28 here. Okay, now we start the examples too. Draw, if possible, a simple graph with 5 vertices having degrees 2, 3, 3, 3, 3. Okay, so let V1, V2, V3, V4 and V5 be the vertices where degree of V1 is equals to 2, and since there is no loop, so V1 must be connected with 2 of the rest vertices. Since there is no loop, as it is a simple graph, so V1 must be connected with 2 of the rest vertices, say V2 and V3. So removing V1 with all its incident edges, we have the graph with V2, V3, V4, V5 where degree of V2 is equals to degree of V3 is equals to degree of V4 is equals to degree of V5 is equals to 3. So it can be drawn here Okay, this way, that means the required graph is V2, V3, V4, V5. So V1. Now this is the required graph. Okay. Here degree of V1 is equals to 2 and degree of V2 is equals to degree of V3 is equals to degree of V4 is equals to degree of V5 is equals to 3. Okay. Now another examples. If a simple regular graph has n vertices and 24 edges, find all the possible values of n and draw a graph against each of such values. Okay, so here let k is equals to degree of every vertex. Okay, therefore the sum of the degrees of all vertices is equals to n into k, as it is the number of vertices n and number of degree of each vertices is equals to k, so sum of the degrees is equals to n into k. So here n into k is equals to 24, 2 into 24, as we know that sum of the degrees is equals to 2 into number of edge. So n into k is equals to 2 into 24. That means n is equals to 48 by k. Okay, and we know the maximum number of edge in a simple graph is n into n minus 1 by 2. Okay, so as the number of edges is 24 here, so n into n minus 1 by 2 is greater than is equals to 24. This is the maximum number of edge for simple graph. As it is given here that it is a regular graph, that means here number of edges may be greater than is equals to 24. Okay, so we have here n into n minus 1 is greater than is equals to 48. So this is the equation number 2. Now k is a positive integer. So from 1, when k is equals to 1, implies that n is equals to 48. Okay, so and which satisfies 2, because 48 into 48 minus 1 is greater than is equals to 48. Okay, that means 2 satisfies here. And when k is equals to 2, it implies that n is equals to 24. Okay, then 24 into 24 minus 1, this is also greater than is equals to 48. Okay, and when k is equals to 3, this implies n is equals to 16. And we know 16 into 16 minus 1, this is also greater than 48. 2 satisfied. When k is equals to 4, then n is equals to 12. Here 12 into 12 minus 1, it is also greater than is equals to 48. When k is equals to 5, then n is not integer. Okay, so it's not satisfy here. When k is equals to 6, then n is equals to 8. So 8 into 8 minus 1, 8 into 7, that is equals to 56. This is also greater than 48. Okay. Now when k is equals to 7, here n is not integer. When k is equals to 8, then n is equals to 6. Then we get 6 into 6 minus 1. What is 6 into 6 minus 1? That means 30. This is not greater than 48. That means 2 does not satisfy here. Okay. So next you can put here n is equals to 9, but n not equals not an integer. N is equals to 10, this is not an integer. N is equals to 11. If you put here n is equals to 12, then k is equals to 4, but 4 into 4 minus 1, that means 4 into 3, 12. So all these values after that are less than. Okay, so the possible values of n are, first is 48, then 24, then 16, then 12 and 8. Okay, so number of vertices should be this. Now we have to draw, you have to draw the graph with these vertices. Okay, this is your homework. Okay, you can draw it. So this is our, this chapter is complete here. And next in our previous lecture, in our next lecture we discuss about the matrix representation of the graph.